topic is GP lens management of the high astigmatic patient, and I'm really excited about who our speaker is tonight, and he's well qualified to talk on this subject. He's been in private practice in Dallas, Texas for 25 years, specializing in vision rehabilitation through contact lenses, as well as cornea disease management, optometric medicine, and refractive surgery. He's a contributing editor for Contact Lens Spectrum. He's an advisory committee member of the GP Lens Institute, and he's program chair of the section on cornea, contact lenses, and refractive technologies of the American Academy of Optometry. And he is, of course, Dr. Clark Newman. So Clark, welcome, and I'll turn it over to you. Oh, and before Clark begins, a reminder that we'll have a couple of breaks during, or at least one or two during the presentation, and there is a questions box that you can input questions and write them in, and when we take our breaks, we can have those questions answered. Also, there's certainly the opportunity, if you want to say something verbally at the breaks, to do that as well. But if you do have a question, you can enter it in the question box on your right, and we'll answer those during the breaks that we're taking. Thank you very much for coming tonight, and Clark, I'll turn it over to you.
Okay. Well, I think what we'll do is just start, and first let me get the conflict statement out of the way. I am an advisor to a few things, as Ed said, and I do have some paid capacities in the industry, so it's important that you know those. But basically, what we're going to talk about tonight is something that I think is very important. And I was fortunate enough to have Irv Boris as a professor when I was in school, and one of the things that he said is that as you advance the scope of optometric practice, don't leave a vacuum. Someone will fill it. And this is one of the areas that we seem to be leaving a vacuum in. And I hope that some of the people that are on this webinar tonight are younger, because that seems to be where most of the education is lacking in this regard. Let's see. What's the point of using rigid lenses to address these issues? One is to address, because when we're looking at rigid lenses, we have geometry issues and we have optics issues, and sometimes we have to get to one to correct the other. And so our main problem is correcting residual astigmatic errors, but the other is correcting poor physiological alignment, and it's important that we understand how to do that. Some of the information that we don't really think about much is if you go through the data that's out there and you look around and you hem and haw through all the numbers, there are a lot of patients out there that could benefit from toric correction of some kind, probably a lot more than we're prescribing. And if you look and distill it all down, the number of patients that could be candidates for RGP toric lenses in one form or another is about 30%. And so if about a little less than a third of the patients you're prescribing rigid lenses for are not wearing torics, you probably aren't utilizing them enough. And that there's also a huge untapped market, because there are a lot of patients that don't see well through soft toric lenses that see a lot better through rigid torics, and they might be good candidates to switch across. Okay, it all translates into a lot of dollars, because these are specialty lenses and you should be charging appropriately. There is a lot higher return on time and investment in specialty lenses, whether we're talking about multifocals or we're talking about torics or we're talking about sclerals for vision rehabilitation or keratoconus or things like that. So this is a very profitable enterprise if you value what you do. I mean, one of the biggest problems that we face in contact lens prescribing, particularly rigid lens prescribing, is that there's a perception that it's not profitable. And sometimes that perception becomes a reality because the practitioner doesn't value what they're doing, and they undercharge for what they're doing, and they don't make enough money at it. There's the old story that I've told several times in my lectures about Joseph Lister, who was a physician who had to remove a chicken bone from a guy's throat, and the guy was really grateful afterwards. And he said, what do you think a good fee would be? And he said, well, half of what you'd be willing to pay me if that bone were still in your throat. And I think that's how we should be thinking about what we do. When you have a skill that nobody else has, being able to affect that skill to the benefit of the patient is valuable, and we tend to be the ones who undervaluate that benefit the most. Okay, let's just say we need toric lenses and they can be profitable in our practice. All right, the questions stay the same, but the answers change. What just happened there? Okay. There are many things that when I was in school, I used to talk to Dr. Borsch about that we wish we could do. Really complex geometries on lenses. And you know, the concept, the envisioning, the imagining of those designs have been around for longer than I've been in practice, and I've been in practice quite a while. What has changed is our ability to make those fantasy designs, and some of the newer computer-controlled lathes can manufacture very complex geometries that we could only dream about when I was in college. So, and the other thing is we can reproduce them. You know, when I was in school, we used to crimp buttons to create toric rigid lenses, and you could get that magic lens, but boy, you couldn't repeat it. You couldn't make a second one or a duplicate. But now you can with a very high degree of fidelity. These 6-axis lathes can produce lenses in such a way that we almost really need to start thinking about changing our terminology. When someone talks to me about an A-sphere, I want to know if they're talking about a lens that has a toroidal surface or not. So you'll see me use slightly different terms than you're probably used to using, and I think it reflects the newer types of lenses that we can use, because a bunch of the toric lenses that I make in my practice have aspheric curves instead of spherical curves in each of the meridians. That's something we can do. We can slab off lenses. We can make lenses so fine that they require almost no polishing, and that really creates high quality control over peripheral curves and things that we used to kind of think we were getting what we thought we were getting, but we really weren't, and that was part of the variability in the system. All right, the corneal surface, is very important that we understand what we're dealing with, and I think that when you look at a cornea, you need to look at central and peripheral toricity. I kind of break it down in my mind that way. Now, you'll see some photographs in this lecture, and essentially everything in this lecture is the left eye of one patient. And you'll see how we go through and make things work. Now, if you look at this is a picture of his cornea. You can see his visual axis is not along the geometric axis of this cornea. They're significantly displaced, and you'll frequently see that. But you need to get in your mind the concept of central versus peripheral toricity. Here is a topography of a patient that has roughly central toricity here in the middle, but if you look around the edge, you see that there is almost spherical curves in the periphery. Now contrast that with our patient who has edge-to-edge toricity. His corneal toricity goes from center all the way out to the edge. Now, when we use a topographer to design lenses, we use some of the information from it, and I think that it's important that we understand what we're getting, and we're just going to gloss over this because this is not really a topography lecture, but it's a rigid lens lecture, but it's very important that we understand this. There are several different views that we use. One is the maps that express diopters of curvature, and I think it's very important that we understand the difference between diopters of power and diopters of curvature, because diopters of power involve radius and index. I can take a topographer and create a map of the diopters of curvature of a rock that I find on the side of the road, but you can't do a refractive power map of that rock, and it's different because the measurements that we see off of a keratometer are diopters of power, not diopters of curvature, and it really gets us into trouble sometimes, particularly when we start thinking about peripheral corneal curvatures. And there are basically two maps, the axial, or what's called the sagittal map. The other map is the tangential map, which is also known as the instantaneous or meridional. Almost no one uses those terms anymore, but you will see axial and sagittal quite often. The refractive power maps are good for estimating total refractive astigmatism, but they don't help us much when it comes to looking at the geometry of the front of the eye. And I think that's a very important point for me to make right now, is that I consider the back of a contact lens a geometry problem, and then the front of the lens is an optics problem. So we have to align the lens first before we can even think about the optics. But we do need to know what the refractive power of the eye is, because it does guide us in what we're doing. There are some other useful plots, numericals and keratometric views, and there are contact lens designing programs which, depending on which topographer or tomographer you have, are more or less sophisticated. I have a Pentacam, and so the one I've got is very sophisticated. You also get some pretty good fluorescein pattern simulation if you want to try several different virtual lenses on a patient while they're not even in your office. It's a good idea to have one of these. Here's an axial map of our patient. This is using my old Humphreys placido base. It's in diopters of curvature, and one of the things you got to understand is that the farther away you get from the center, the less accurate an axial map is, because of some of the assumptions that are made in creating the extrapolations in an axial map. But it's the most reproducible. But if you want to look at small, sharp changes in curvature, like keratocone, this probably isn't your best map. This is the axial or sagittal map on my Pentacam for the same patient. And here is a tangential map. These are more accurate in the periphery, and they also show very good curve changes if there is a local change. And this is the best one to use for contact lens design. As you approximate the center of a topography, and you have to remember, the center of a topography is not the geometric center of the cornea. It's along the visual axis as they line up down the sighting of the instrument. So sometimes the geometric center that you're trying to align geometrically with the back of a contact lens is not the point that's in the middle of your topography. And it's important to remember that. But this is the one that we use for contact lenses mostly. There's some debate about that, but I think I've got some pretty good reasons why. If you look at the way in which the axial and the tangential maps are created, as you approach the center of the topography, the data from the tangential and the axial maps become the same, because the assumptions that limit the axial map in the periphery are not there in the center, and the tangential map doesn't have those limitations. So the center of a map is virtually the same whether you're using a tangential or a sagittal map. Here's the tangential map of the same patient on my Pentacam. One of the things that's interesting, if you look at these two views, let's go back for just a second at the previous view. It looks like the topography shows the astigmatism going edge to edge. But if you count these squares, the image that you see here is much smaller. This is a millimeter grid, and when you go to the Pentacam and you look at the scale along the bottom, a Pentacam images an area that's almost twice as big. So what happens is the image that you would see on a placido-based topography is about right here where my little arrow is going around. So you get a lot more information. I mean, this is scleral curvature out here on a Pentacam that you just don't get with a placido system, and it's very accurate because it's all elevation. And we use it to design sclerals, which sometimes corrects astigmatism. This is a contact lens module from the Humphreys. The newer version of this module is a lot better than what I had. This is my older one. But you can see the simulated fluorescein pattern. And keep this picture in your mind as we look at some of the fluorescein patterns on this patient. This is the exact same patient looking at the fluorescein simulation in the contact lens module of my instrument. Now, I don't use these programs much because unless I really am struggling to find an alignment, I can go over here and change my numbers, my base curves and everything. And these instruments also have huge databases of proprietary designs in them already that you can use to simulate these patterns. But you can see that this fluorescein pattern shows that this patient has a significant amount of toricity. And when you look at a lens on the eye, that's a pretty good correlation between the fluorescein pattern and actual fact and the simulated pattern. All right, the posterior surface is a geometry problem, as I said, and we basically have several ways of correcting that. Now, you're used to hearing about spherical curves and toric curves and aspherical curves. But since I can make torics with spherical curves or aspheric curves, we kind of need to change our terminology. And so we have isocurves and we have toroids. And I can have a spherical isocurve I can have an aspherical isocurve, which are called isospheres and isoaspheres, and then I can make toric curves using either spherical or aspherical geometries. So basically, the thing that you think is a sphere, I think is an isosphere. And the thing that you think is an asphere, I think is an isoasphere. And it's important because, and it's not trivial because we do make a lot of torics with aspheric curves now. When do you not use a toric base? Well, and this is my view, and Ed can disagree if he wants, but I think that when there's less than 2 diopters of central toricity, you can get significant alignment that's physiologically tolerable with an isocurve, either isosphere or an isoasphere. I also, when you have almost no peripheral toricity, you got to be a little bit careful. Sometimes it's easier to align with isocurves in those cases. All right. Why does an aspheric lens, we've heard for a long time that aspheric lenses mask more astigmatism. And first off, it's not an urban myth. An aspheric lens does mask more astigmatism, and it's because it has 2 different radii at any point that's non-apical. And most people go, huh? Well, let's look at it. This is an isoasphere. It's an ellipsoidal shape, and right in the center, there's a little bitty area that approximates a sphere, and that's our apical radius. And the point that's right at the tip of the posterior apical radius is our apical point. And what we get in an ellipse like this is you have one radius, the sagittal radius, and then you have the tangential radius. And if you look at those two, the radii are different lengths. Well, isn't that what a toroidal surface is? So if I take a lens that's not on my apical point, but take a point that's off of it, any apical point will be approximating a sphere. Any non-apical point will be approximating a toroid. And the more eccentricity there is in that aspheric shape, the more toricity you can mask. Now, using an isoasphere, because the benefit of the tangential and sagittal radius are only present when the lens decenters, that means it has to be lid attached. And one always wants vertical decentration and never horizontal, so the only time these things really work is when you have with the rule astigmatism. So you use an isoasphere to mask corneal toricity when it's with the rule. Okay, and it works pretty well up to, depending on the eccentricity of the particular lens you're using, it can work up to 2.5 diopters, but usually you want to limit it to around 2. All right, now when we look at toric curve alignment, there are 2 basic ways to do that. One is to take each principal meridian and line them up. That's called saddle alignment. The other is called a low toric simulation. And this is where one principal meridian is aligned and the other is flatter than the corneal curvature. And you've all heard the adage, you fit the flattest corneal meridian on K and the steepest corneal meridian flatter than K. Well, that's not true. That's wrong. Because of this question, and I'll pose this and I'm going to show these to you one at a time, and think about it in your head. What is the best corneal topography for aligning an isospherical lens? Is it a spherical cornea? Is it a width rule cornea with about 1/2 diopter of astigmatism? Is it a width rule cornea of 1 diopter of astigmatism? Is it an against the rule cornea with 1/2, an against the rule cornea with 1, or none of the above? Well, the answer is this one. And the reason why is that when there's a dioptric difference in the vertical meridian, with the vertical meridian being steeper than the horizontal meridian, that's a cornea that lends itself well to lateral alignment and vertical movement, which is what we want in a rigid lens. We want the lens centered laterally, and we want it to move vertically, and with relative ease, because that's what makes a lens comfortable. So our goal when we're trying to create a low toric simulation is to manipulate the alignment of the principal meridians such that we're aligned horizontally and flatter than alignment vertically. So that's our goal. One needs to think in terms of horizontal and vertical instead of flatter and steeper. And if you look at the famous Mandel-Moore guide, it basically does that when we're talking about a with the rule cornea, but it does the exact opposite of that when we're talking about an against the rule cornea. When we're talking about against the rule cornea, the low torque simulation of the Mandel-Moore guide aligns the lens vertically but makes the lens too steep horizontally. Well, that's not what we want. We want it aligned horizontally and flat vertically. I think I said too steep, too flat. All right, a quick word about oblique toricity. If your flat or steep meridian is more than 20 degrees or 30 degrees misaligned with horizontal and vertical, I'd saddle it. I mean, you usually don't get good low torque simulations that way. It just doesn't work well. All right, so basically we need to perform world-class refraction and measure our vertex distance. How many of you do that? I mean, particularly when you have higher powers, it's really important that we measure vertex distance because it needs to be factored in. Take careful keratometric readings, do your topography, and print the view that you think helps you design the lens. I used to have this thing called the contact lens view on my Humphreys topographer, which was a combination of an axial and a tangential and a keratometric view, and then in the last box I always put the keratoscopic view so I could see if there were any irregularities, and that gave me the kind of the data that I needed to look at it. There are a series of anatomic measurements that I think are very, very helpful. One is the horizontal visible iris diameter, one is the vertical visible aperture, and then the position of the lids, upper and lower, relative to the limbus. I also want to know what my pupillary diameters are, and if and I need to know what the lid tensions are. Are the lids loose? Is this an older patient? Are they average? Are they tight? Is this an Asian patient, which is a different strategy altogether? But I'll tell you what, if you give me the refraction and the Ks, and you give me these anatomical measurements, I can design a lens that'll work 95% of the time without ever seeing this patient. So these are the types of data points that you need. So as we go through, this is the patient that we're talking about, and this is his existing lens. You can see how it's dropping down and in. But this is the horizontal visible iris diameter, or the HVID, and that's the vertical visible aperture, or the VVA. And this is the lower lid station. And lid station kind of is a concept that comes out of obstetrics, where the cervix is 0, and above that is plus, and down below the cervix is minus. And what we do is we use the limbus. And if the lid encroaches up on the limbus, then it's a plus number in however many millimeters. And if you see sclera, then it's a minus number by however many millimeters. So the difference in the HVID and the VVA are the lid stations. And assuming that the cornea is roughly round, it almost never is, but basically assuming it is, that's a pretty good deal. So there's the superior lid station. There's your pupil and scotopic and photopic diameters. So let's take a look at this patient in our example. He's -3, -5 at 161, so he's roughly with the rule. His Ks are have a certain amount of toricity in it. His HVID is 11.5. His VVA is 9. His superior lid station, the upper lid encroached past the limbus 1.5 millimeters, and the lower lid up 1 millimeter. And his pupils were 3.5 and 5.5. So we're just going to look at that, use that data set to kind of design the back of this lens. Before we do that, though, why don't we stop and see if there are any questions at this point, because we're almost a third of the way through. So do we have any questions?
Yeah, let me mention a couple, Clark. I know there's a couple on the that our viewers have asked, and I want to make sure that you have those. Let me ask a question. I agree with you. I think around 2 diopters is a good point to start thinking about some sort of back surface toric lens. And topography certainly is very helpful in dictating how you're going to approach it, and particularly if you're going to utilize toric peripheral curves. When you have limbus to limbus, well, let me ask it a different way. Do you automatically go with toric peripheral curves when you have a toric back surface, or do you see if there's limbus to limbus? How do you approach that? Or if I'm jumping the gun, I apologize.
Yeah, I'm actually going to address that in just a minute, because that's an important issue, particularly when it comes to peripheral curves, because one of the neat tricks that we can use is to manipulate the sagittal depth of the optic zone by changing the peripheral curves. and we use that to ovalize the optic zone. But in a general trend, in a general thought, I'm much more prone to move towards a toric back surface now than I would have been in the late 1980s, because my ability to create and reproduce these toric lenses is so much better, and I'm getting what I think I'm getting, where in the old days we didn't, that I go to them sooner rather than later, than, compared to the early days of my career. Does that make sense?
Okay. Very good. Well, one question that we have is, do you have any guidelines for appropriate fees? I assume this would be on for torics. And the questioner goes, I have no idea how to determine what fee is appropriate.
Well, okay, it's a little off topic, but I wrote an article about this sometime late 2009 or early 2010 in my column in Spectrum, where, find out what your chair cost is, and then figure out how many hours you spend getting a patient from beginning to end, and how much chair time is involved with your staff, because essentially your staff is half of your time. So let's say I spend 2 hours and my staff spends an hour. To me, that's 2.5 hours of office time. And then you need to figure out what profit you want to extract from the session, and work backwards from your chair cost, multiplying that times the number of hours, and then adding your profit to that. And that's a rational way of developing a fee schedule for not just torics, but your entire fee schedule. I tend to treat initial dispensing fees. First off, we don't use the word fit in my office. I hate that word. People fit shoes. I prescribe contacts. So we prescribe and dispense contacts, and I use initial dispensing fees that basically get a patient not all the way to the end, but through the adaptation period. Because if you charge or if you base a fee on a time, like 3 months of care, well, if they only come in once, you're ripping them off. If they come in 20 times, you're ripping yourself off, and either one is either rational nor ethical. So I base my model on the medically necessary codes, the 9231 codes, and we get the patient through the adaptation to the lens, and then we charge appropriately for follow-ups thereafter. And I think that's another way to keep your profitability high. The last thing I'll say on this, and then we'll move on, is it's very important that you understand the return policies of all of the lenses that you have, because rarely do guys get chewed up on the professional side of this thing. Where they start losing money is when their cost of goods gets really high, because they're paying for remakes that the patient isn't paying for. So it's very important, particularly if you get into specialty lenses like some of the sclerals, that the patient knows that they're going to have to pay for every lens that you put on them. That's important. Okay?
Okay, very good, Clark. And there's another question, and Clark is one of the nation's experts on coding, and he had a column for some time in Spectrum on that issue alone. So any questions there, I'm sure he'd be very well qualified to comment on. Another question was, what maximum corneal diameter can you analyze with the Pentacam topographer?
Well, a Pentacam images 16 millimeters across the whole thing. So depending on how big your cornea is, you get a little sclera on either side.
Okay. And then also, how do you use those anatomic measurements? I assume that's with the Pentacam. And the question is, I measured them, and
we're getting to that.
Yeah. Okay. Very good. And then one other question was just simply, if using topography to design toric lenses, you might be getting this too, how important is the scale setting, normal, absolute?
You really want it absolute, because the numbers in the millimeters of radius that you're using will be absolute numbers. If you want to see very, very fine changes in contour, you've got to relativize your scale. You've got to normalize it. But in the greater scheme of things, you just want to make sure that the numbers that you're seeing reflect the geometry that you're going to align. That's the important thing. Okay, well, let's drift on.
Very good, Clark.
Okay.
Okay, very good.
All right. Okay, so let's take this patient again, and We can calculate residual stigmatisms. I'm not a real fan of it. I think we all know how to do that, but it's in here, and since this lecture will be up on the thing, you can take a look at how we'll do it. But for this particular patient, we're going to have, there's a difference between the corneal curvature and the refractive. He's got 5 diopters of refractive. He's got a little over 3.5 of corneal, so there's going to be a little bit left over in the mix that we're going to have to address optically. All right, now, you asked me a question about how do I use those numbers. Well, if I have negative station numbers, particularly in the upper lid, it's very hard to lid attach. If I have negative numbers in the lower lid station, it's very hard to do a translating bifocal on a patient like that. So, most of the time when we're talking about low toric simulations in torics, we want to lid attach these lenses if we can. We can't always, but that's our goal. And so we want positive lid station numbers on the superior. I have, over the years, created what I jokingly call the feng shui of lens parameters based on the HVID. Now, this is assuming a relatively normal corneal eccentricity. If a patient has a very round cornea where their eccentricity number is very low, these numbers have to be adjusted, as they do if the numbers are very, very high. And now how would you infer that? Well, if you have a relatively large corneal diameter and the corneal curvatures are very flat, then they have to flatten rapidly, so that's going to have a high eccentricity. If they're very, very steeply curved, I'm saying that backwards. If they're very steeply curved, to get to that wider diameter, they're going to have to flatten quicker, so you're going to have a high eccentricity. If they're very flat, you're going to have a rounder curvature, and your eccentricity will be low, and vice versa on the lower end. If you've got a very small cornea and very steep curves, that can be a fairly round eye. If you have a small cornea and very flat curves, they're going to flatten rapidly. So this is assuming the normal eccentricity of about 0.6, which is good news because it works on about 90% of the patients. And I basically get most of my lens parameters from just picking the HVID. So when we look at our patient, he has an HVID of 11.5, so I'm going to select the 9.6 diameter lens. The optic zone is going to be 8.0. The anterior optic zone, or what's called the lenticular bowl, will be 8.4. And then I have my horizontal and my vertical fit factors. Now, the reason why we go flatter than the corneal curvature is because the lens is basically a diopters of curvature issue, and the keratometric readings are diopters of power. And so we have to compensate a little bit to make that work. And so even though we want to achieve alignment, we have to make the lens a little bit flatter to get the sag relationships right. So we're going to flatten the horizontal meridian, but basically what we're trying to do is achieve alignment. And across the board at the bottom, you'll see the difference between the horizontal and vertical fit factors is a diopter. And that's our 1 diopter of low toric simulation. So the vertical is always a diopter flatter than the horizontal. And you can see that. So you've got all your horizontal fit factors here and your vertical fit factors. Now, when the patient has with the rule astigmatism, you'll do this just like you would with the Mandel-Moore guide. You flatten the horizontal meridian, you flatten the flat meridian, and you're a little flatter than that in the vertical meridian, and you just compensate for your powers. When you have an against the rule cornea, you have to think about the numbers a little bit more, because the steep meridian is the one you're going to be aligning up. And when you have alignment, the power is going to be correct. You don't have to compensate. And it's going to be the vertical meridian that's a little bit flatter, and you'll have to adjust the power of the vertical or the flatter meridian. So, basically just put it on the deal. Now, I will supply to the GPLI a little worksheet that I have put together that makes this very simple, makes it very easy. And I'll get, we can use it as a resource. We'll just put it up on the net. It's a deal just like the Mandel-Moore guide that allows you to fill in the things, but it shows you how to do it using this horizontal and vertical stuff. Okay, same deal here. You algebraically compensate whether you're making, just blow it up in your head. You've got your 2 powers, you've got your 2 meridians, the horizontal ones align, so whatever power you've got acrossways is going to be whatever it is, and the vertical power is going to have to be compensated. Let's use our example. This guy's a -3, -5, so you've got powers that are -3 by -8. You've got a horizontal curvature of 4375 and a vertical of 4737. So our radius in the horizontal is going to be 784, and we'll compensate our powers because we flattened the meridian just a little bit. The vertical meridian is going to be, we've got our -8. We're going to be a little flatter than the 4737 by a little bit, and we have to compensate that as well. This is just one of these things you just have to do this, and the way to do it is put it on the optical cross, put your meridians, put your powers, and just calculate them out. So if we go with our example, we've got a lens that has a radius of 784 -225 by 739 -550, and it's very important that you specify back vertex drum readings. This is very important for two reasons. One is the 6-axis lathes think in front vertex, so whenever a power is given to them, it has to be converted. And the drum readings make sure that they're not misunderstanding that the 550 is the amount of toricity, but the true power in that meridian. And I'll show you this in just a second as we go through it. But I always tell the lab back vertex drum readings. It saves us a lot of problems. Now this is the spherical lens that this patient wore in originally, and it's all over the road. It decenters. In this photograph, it's off to the left. In this photograph I showed you before, it was off to the I'm sorry, it's off to his ear, and the other photograph is off towards his nose. So it's rolling all over the place, and it's bearing really heavily right here. So this is the lens that we designed that finished up. Now, again, it's a little bit decentered laterally, but the optics are right in front of his line of sight. Because if you remember back to the original photograph, this guy's line of sight is way off his geometric axis. But it's a lid attached lens, so the lower lid's not banging into it. And if you see this fluorescein pattern, I've got a little bit of clearance here in alignment this way. So that's simulating that low toric simulation of about a diopter. This is probably simulating a little bit more than a diopter, maybe a diopter and a quarter or a half. But what we did was we created a lens that moves vertically and centers laterally. All right, in the future, and if you look at my Spectrum article next month, it'll be on splines. Splines are really important to understand because they are allowing us to do all kinds of different things. One of the things that we've done so far is we've assumed that all the hemimeridians are the same. If I look at the center of my lens and go to 12 o'clock, I'm assuming that the curvature is the same as it is going to 6 o'clock. But what if that's not appropriate? What if I need a steeper meridian at 6 o'clock than I have at 12 o'clock? Well, spline curves are the answer. And you see these now in the quadrant-specific lenses that we use to correct pellucid marginal degeneration. It's also the way in which multifocals are made. By using spline curves, we can have very high eccentricities that create the optics that we need and then bring the edge back down so it doesn't stick off the surface of the eye. The Essentials multifocal is one example of that. Spline curves are also used to design every progressive edition spectacle on the market, particularly the newer freeform ones. All right, Ed mentioned earlier we can have different shapes to the peripheral curve sets. You can have a single curve set. You can have toric peripheral curves as well that are either spherical or aspherical. But what does that do? Well, let me impart this thing. This used to be more true than it is now, because what we used to do is make a lens and modify it until we got it right. And everything that I have in my designing systems allows me to remove plastic to solve my problems. If you make a lens too flat or too small, you've got nowhere to go but to do another lens. But if you make a lens a little bigger, if you make it a little thicker, if you make it a little steeper, you can always flatten it, you can always cut it down, you can always thin it. So you can solve your problems by removing plastic. And so the strategies that I use always are aligned with Dr. Boris's comments. All right, peripheral curves. You can have an isocurve base curve with a toric peripheral set. You can have a toric base curve with an isocurve peripheral set, which I don't use at all anymore because that's old thinking that I think applies more to hand-applied peripheral curves than numeric control lathe cut peripheral curves. So I don't do that at all. But the one at the top, I do a lot, and I'll show you why in just a second. If I have a toric base and a toric peripheral curve set, my optic zone's round. But if I use an isocurve base and an isocurve set, my optic zone is also round. But if I use an isocurve base and a toric peripheral curve set, you see how it ovalizes the optic zone? And that changes the sag radius across here and here. Even though I'm using the exact same base curve radius, it does create a difference in the sags here to here. So I create a toric simulation without using toric optics, or toric curves rather. Now I get the same thing if I use a toric base, but I put isocurve peripheral curves. Well, I don't think this is good, because if I'm using a toric base, I'm already altering my sags, and I don't want to screw that up by changing the optic zone diameter to an oval or shape from an oval to an oval from a sphere. So this is another reason why I never put isocurve peripherals on a toric lens. I just don't ever do it. Every toric lens we make has toric peripheral curves. And considering we can cut those toric peripheral curves with extreme fidelity and they're highly polished even before you put them on the balloon polisher, there's no excuse for not doing that anymore. But when a patient has a significant amount of peripheral toricity, even though they don't have a lot of central toricity, man, you can put a toric peripheral curve on a lens that's spherical and really change the edge lift and compression all the way around. And it can make a lens so much more comfortable. So we use toric peripheral curves with isocurve bases a lot. All right. Any questions about that, or did I just blow everybody away?
No, I think that's great, Clark. I think what you're doing is giving us really a peek into what the manufacturers can do today. You know, it's in the day when Dr. Borish lectured to both of us, you came away feeling that you knew that he knew torics. The torics were very baffling. It was difficult for manufacturers to make a real accurate toric. The thought of bitorics, you know, and now you're going in more modern designs and what you're being able to do, particularly with the peripheries, and that's pretty remarkable. No, I think it's great. I'm going to stall for a minute to see if we have any questions, but in the interim, you know, we would love to have your worksheet. I think that'd be a nice addition to what we have on our website. And that's a good segue to mention that we do have several tools as they pertain to toric design. And we have our new toric and spherical lens calculator. And the toric calculator is very dynamic. It was designed by Tom Quinn. And if you haven't used it, you know, it's right on the front page of the website, the home page. And go in and try it out, and it'll design torics. If it's a low astigmat, it's a pretty good empirical calculator for spherical designs. We also have the Mandel Moore calculator on the website. We do have a GP case gram rounds troubleshooting guide that has a lot of cases that pertain to toric lenses that I think you'd like, and then we have our GP clinical pocket guide. So that's my commercial for tonight, but I think when Clark mentioned that he has that worksheet, which I think would be we'd love to have it, Clark. Thank you. It would be a really nice addition to the website. That would be one of several tools that hopefully would be helpful to you. And with that, Clark, I don't think there's any questions. I think you can go on ahead.
Well, all right, this is where we start dealing with the optics. Once we have the alignment of the back surface of the lens, we need to start thinking about the anterior surface. And that's our optics problem. Right in advance. There we go. Okay. There are several different toric lenses out there. You know, we've talked about toric bases, but what if the corneal curvature is roughly spherical, but the patient has a significant amount of residual astigmatism? Well, a front toric lens can be very helpful in correcting that situation. A couple of things that I like to do, I like to use larger diameters than my normal guide. I also like to decenter the posterior optic zone a little bit, and you can do that with a computer numeric lathe. You can make your optic zone not centered in the lens. And the reason why I do that is because these lenses tend to drop a little bit, and the optic zone sometimes isn't where it needs to be. It's also helpful, as you'll see in a minute when you start seeing how peri-ballasted lenses are created, that if you move your optic zone, it helps put the optic zone back where it belongs. What is a peri-ballasted lens? Well, there are two ways of there are three ways of stabilizing a lens. One is a prism ballast, one is a peri-ballast, and the third way is a dynamic stabilization. And there are two of those out there right now that are used. One is a thin zone design, and the other is the bump design, where you put these little bumps on the lens, and that doesn't work well in an original lens, but it works pretty well in a soft lens, and one of the designs that has that is the Air Optics toric. But you can do all of those with spline curves, and you can do the peri-ballast fairly easily. The reason why I prefer peri-ballasting a lens to prevent rotation over a true prism ballast is because a prism ballasted lens varies in power from the apex to the base of the prism. And depending on how much prism you're using, it creates a significant power change through the sweep of a lens, and that creates variable vision. Peri-ballasted lens does not have that problem. So how do we create a peri-ballasted lens? Well, what you do is you create your optic zone, and then you create your ballast zone, which is the original minus carrier around the outside of the lens, and then you cut the diameter of the finished lens off center, so that the optic zone, you can see how the optic zone rises in the lens, because now all this stuff at the top is going to get cut away. And now we are thicker here than we are here, and that's how we create a prism-like ballasting zone here, but we don't have a problem with the optics being non-coaxial. The axis, the normal axis of the back surface and the normal axis of the front surface are in line with each other. They're coaxial. In a prism ballasted lens, they're not. The front surface is angled outward, just like, if you look at a prism, the two surfaces are at an angle to each other. So we end up cutting off that, and then that's our finished lens design. Okay. One of the things we can do, as I said, is there's no induced vertical prism. So if we're, that's another thing, is there's no induced vertical prism. So if we're prism ballasting one lens and not the other, we don't create an image jump. And there's no power change across the lens. Also, if you put a small offset lenticular at the bottom of the lens, you keep it a constant edge thickness. The one disadvantage of peri-ballast is sometimes it's not enough to create rotational stability. But what is a offset lenticular? Well, if we take the bottom of the lens and slab it off, we end up with a constant edge thickness all the way around the lens. And if you look at this picture in your mind, this is the exact lens design of almost every toric lens that Cooper makes. All the Hydrosoft torics and the old Sunsoft torics. I know that's not a Cooper product, but those were, and the Western opticals. Those are all the same concept with the peri-ballasted offset lenticular. All right. During a blink, the lower lid action is to move nasally, which causes the bottom of the lens to rotate. Therefore, one needs to order the prism rotated usually nasally. I almost never order a prism, whether it's peri-ballasted or not, straight down at 90 degrees. I almost always turn the base of the prism towards the patient's nose, so that the right eye is along the 110 axis or the 100 axis, and the left eye is along the 75 to 80 axis, somewhere in there. And for higher minus lenses, you need to increase your prism, a little less for plus lenses, and decrease your prism for materials with really high specific gravities, and increase it for really low specific gravities. Some of the materials out there are very heavy. Most everything that Polymer Tech makes is pretty heavy. Almost everything that like all the fluoroperm lenses, those are pretty light. and so you have to think about changing your prism accordingly. All right, placing a prism ballast on a lens. If the cylinder axis is across here, the prism axis is oftentimes at 90, but I might rotate it on this left eye to be along the 85. So I've rotated it 5 degrees. Now, truncation. If you truncate a prism ballasted lens, you reduce your prism. So if you want to end up with the same amount of prism you started with, you have to put a ton of prism in there. And I don't recommend that. So if you're going to truncate a lens, minimize your prism as much as possible. So if you're truncating a minus lens, you're going to decrease your prism. The opposite is true for a plus lens, and so you have to, again, think about adjusting your prism to account for whatever it is you're truncating. Okay, rotate your truncations also. You don't have to truncate 90 degrees to the prism axis. You can turn it a little bit, and that sometimes will help also prevent rotation. All right, a lens that we don't use a lot of is a toric base with a spherical or an iso curve front. It's also called the base toric or the back toric. And it's only useful under certain conditions when the total residual astigmatism is roughly 1/3 greater than the delta K. So if a patient has 2 diopters of corneal curvature and they have 3 diopters in the glasses and it's lined up, then you can get away with using a base toric. However, that induced cylinder that you correct with a base toric, it's index dependent, and I'm going to show you that in a minute. And this is not a trivial thing. If I told you that the way to make a thinner toric lens is to use a low index material, most of you go, no, Clark, that's wrong. But it's actually correct, and I'll show you why in a minute. It has to do with this induced cylinder. All right, induced residual astigmatism. Because the index of refraction of the tear film is different from the index of the lens, a toroidal posterior surface will induce a cylinder that has to be accounted for. And it's index dependent. And the greater the induced cylinder, the greater the cylinder has to be on the front of the lens, which makes your junctional thicknesses greater. Because unlike a spectacle lens, we maintain our center and edge thicknesses constant by specifying them, and what changes is the junctional thicknesses at the lenticular. And if you have a bigger cylinder to compensate, you make the junctional thicknesses greater, and that's why it's better to use a low index material on a toric lens, because you'll induce less cylinder, which means you compensate less cylinder on the front, and that makes your junctional thicknesses less, which makes the lens weigh less, which makes it easier to control. It's just better all the way around. So, rule of thumb, for multifocals, use high index materials. For torics, use low. Okay. Let's look at this, for example. The high watermark used to be 1.49. With the newer high index lenses, we now have 2 lenses that are above 1.5, and they're great for bifocals, but I wouldn't make a toric out of them. The mid ranges are your fluoroperm materials and your Fluorex materials, and the optimum materials. Essentially, here's another rule of thumb: anything Polymer Tech makes is a low index material. All their lenses, whether we're talking about XO, XO2, ES, EO, RXD, they're all low index materials, and so they're my go-to materials for torics. All right, I'm not going to bore you with this formula, but if you look at it, a 1.49 lens induces half the delta K. A lens that has an index like a Boston lens induces 1/4 of the delta K. So we've cut the amount of induced cylinder in half relative to a higher index just by going to a lower one. And that's one of the reasons why I like using low index materials. All right, so again, yeah, EO induces half the astigmatism. The power of the lens in air is also dependent on the index, and so it varies as well. Same sort of thing here, and we all use, those of us that are older learn the rules of 1 1/2 and the rules of 1/2, but those rules only apply to 1.49, which is PMMA. The lower index materials induce a lot less. All right, so there are the last class of lenses are bitorics, and we have spherical power effects, we have cylindrical power effects, and then there's one that's very rarely used that most people don't know about, and it's probably going to be a column of mine in the near future, is the cross-cylinder effect bitoric. Now we'll go into why we would use each of these. Let's start with the spherical power effect. This is a workhorse lens for us when it comes to correcting astigmatism. It's a very exquisite design. It was originally conceived by Mort Sarver back in the day. And essentially what we're doing is we're putting a cylinder on the front of the lens that compensates for the induced cylinder on the back, so that the lens has toric optics but acts like a sphere. So if the lens rotates a little bit, it doesn't matter. The lens corrects. And the neat thing about this is that if you look at the data, is that the more astigmatism a patient has, the more likely it's all to be anterior corneal. So these are great lenses to have. When the total astigmatism is equal to the delta K, if they have 4 diopters of cylinder in their glasses and they have 4 diopters of cylinder on their cornea, then it's all anterior corneal, and a spherical power effect lens will solve their problem. This is also a very neat concept for developing toric trial sets. I know that Ed advocates this in his book, that having a spherical power effect toric trial set is the way to go, because you don't have to worry about the lens rotating. You know exactly what it's going to be when you do your spherical over-refraction or your sphericylinder over-refractions. You just add it to the lens. It's a very exquisite thing to do. I have 3 of these SPE toric trial sets. All right. I think I just already covered that as I was talking along. A large proportion of the bitoric candidates can wear an SPE, so that should always be something that we're thinking about. Now, here's one of the neat things about using either a Mandel-Moore guide or the guide that I use, is you don't even have to consider this. It's going to be whatever it is. It'll come out in the wash. As you calculate, it'll do just what we want it to do. The cylinder power effect lens is indicated when an isocurve lens demonstrates poor physiological alignment and there is a significant physiological residual astigmatism. So a spherical, if I put a spherical lens on, it looks bad and they see bad. You know, in a scenario where a patient needs a spherical power effect lens, the lens looks bad to the doctor, but the patient can see out of it. So here, neither one is good. Now, our example that I use tonight is an example where we will end up with a significant amount of residual astigmatism. So this lens ends up being a cylindrical power effect lens. Now, what is a cross-cylinder lens? Well, a cross-cylinder lens is not something we could make prior to the computer-controlled lathes. There's a significant proportion of the patients out there that you try a toric lens on, they never can see out of it. And the reason why is because this patient has a corneal toricity that's significantly different from their spectacle cylinder axis. If there's a 15 or 20 degree misalignment between the spectacle cylinder axis and the anterior corneal toricity, there is a cylinder on the inside of the eye that's changing everything. And then when you mask the cylinder on the front of the cornea, we now have an obliquely crossed cylinder inside the eye that's non-compensated. So you can put a toroid on the front of the lens that's not lined up with the toroid on the back. And this is a great place to use an SPE trial set, because you can figure out what your alignment is, and then whatever the spherocylinder over-refraction is, they just add it to the lens. And trying to use just a backdoor trial set with these is a nightmare. So I only know of about 3 labs that can do these. Fortunately, one of them is right here in my area. And you know, if you're going to talk to a lab guy and you ask them about a cross-cylinder effect lens, if they don't just say, "Oh yeah, I know what that is," don't order it from them. find another lab, because there are labs out there that are good at making these things, and boy, do they solve problems. Okay, when you're ordering a lens, you got to order your overall. I don't leave any power or parameter to the lab. That's them doing my job. So we specify everything: overall diameter, optic zone diameter, anterior optic zone, base curve radiuses, both 1 or 2 if it's a toric or not, whether they're A-spheres or not. I specify the eccentricities. The lens powers, we specify meridian by meridian, and again, we get back to that back vertex drum reading issue. Let's look at our example for a second. This is how we can get into trouble with power. In our example, the back vertex power readings were -525 and 550, and that can be expressed as a -225, 225, and 161. However, if one gives the lab these two powers and doesn't tell the lab that they're drum readings, you might get a lens that comes out differently, and you can be off by 3 diopters or whatever. So they need to know that these are meridian by meridian powers is the other way to think about it. And they do need to know it's back vertex because the lays think in front vertex. All right, overall diameter, optic zone, base curve radius, the powers, the center thickness. I like to use the minimum center thickness per the material manufacturer. If we're not trying to bend the lens, and that is another way that I used to use more often was something called control flexure, was I would make a lens intentionally thin so that it would bend on the eye. I don't do that much anymore because I'll just as soon go to a toric. But I like to specify the center thickness as thin as possible according to manufacturer specifications for that diameter and material. I like to specify my edge thickness, and I've got to have enough of an edge, enough of a minus carrier lenticular to create my lid attachment if I'm trying to do a low toric simulation. I really need to have that. So I like to specify them in the area of 0.13. I think any thicker than that, you start running into comfort issues. You also start running into desiccation issues because you start holding the eyelid wiper away from the lens surface, and you're not massaging the eyelid with the wiper. Then you got to specify your peripheral curve sets. I use mid-range decays in these because in the mid-range decays I get stiff materials with low indexes available to me. My ideal lens for a toric would be a very stiff lens that doesn't twist when you, because if you're trying to carve toric surfaces, you don't want the button twisting, and some of the less dimensionally stable materials will actually twist in the lathe, and then the optics aren't as good. So I want a really stiff material for 2 reasons. One, I don't want it twisting. The other is I don't want it flexing. If I'm going to go to the trouble of calculating the delta radiuses, I want them to be that and not whatever the lens flexes to. So I use stiff materials for this. I use low index so I get thinner lenses. My ideal scene would be to use a low specific gravity material. The problem is to get to stiffness and low index, the Boston materials have pretty high specific gravity, so they're pretty heavy. But they're not the lowest in the world, and so sometimes lens mass, particularly if I'm making a really thick plus lens, I might not use a Boston material because the gravity, specific gravity of these lenses is so high, the lens might drop and I can't maintain my lid attachment. So, if I'm doing a minus lens, I'm pretty much using a Boston lens. If I'm not, I'm going to a lens that has a lower specific gravity like a Fluorex material. Okay. One of the things I like that's really cool is that most of the really good labs now can laser etch a lens surface. They can put they can mark the axis of the flat meridian, and my lab does it by writing the axis number on it. So if you put your base at 90, he writes 090 on the lens with a laser. If you put it at 85, you put 085, and you know exactly where it is. So you know exactly where things are lined up. So pick a lab that has the capability to laser etch on your lenses, because when I do a cross-cylinder lens now, I have them mark both sets of meridians, both the back surface and the front surface. You can really tell where you are that way. You can tell if your lenses are rotating. And then verify the lens parameters. Okay, the dispensing visit, one of the things that I like to do is I do not assess lens movement or fluorescein patterns by putting somebody's head in a phoropter. I'm sorry, in a slit lamp. That's not a natural head posture. When a patient's leaning forward with their chin up, the lenses behave totally differently. They'll rotate, they'll flex, they'll lag, they'll do all kinds of things. So if I'm looking at lens rotation, whether it's a soft lens or a rigid lens, or if I'm looking at bifocal segment alignment and rotation, I evaluate it first outside of the slit lamp. Now, I do look at fluorescein patterns both outside the slit lamp and then at the slit lamp because I can see how the junctions bear at a slit lamp that I can't see with a Burton lamp. But a Burton lamp is an invaluable tool. And if you don't have a Burton lamp, you've got a plus 20 diopter lens. They make these little LED blue lights that you can get at REI. Go get one of those, and you can excite the fluorescein that way. And what I'll do sometimes, if I'm too lazy to grab my Burton lamp, is I'll grab a 20 and my Rattan filter and hold it up together and then shine the blue light at them. We've got those in all the exam rooms. But try your best to evaluate lens movement, lens centration, and positioning outside the slit lamp. These little Rattan filters are great. You can buy these from any of your labs. I think they're great to have. I've had them on my slit lamps for years and years. All my new slit lamps have the Rattan filter built right in, and I just hit the button and I've got a Rattan filter in there, and that's kind of the way to do it. This is another very important thing for me, is that when I evaluate fluorescein patterns, the pattern that I see needs to be the same. It needs to mean the same thing every time. And so if you come to my practice, one of the things you can't not find anywhere in my office is a fluorescein strip or a rose bengal strip or a lissamine green strip. You cannot find them anywhere because I don't have them. What I do is I compound fluorescein in syringes. I have my pharmacist do it, and it's 3/4% fluorescein, and we use these little sterilizing filters, inline IV filters on the tip, and that helps regulate the amount I put on the eye. It also sterilizes it. So these are non-preserved, so I don't have preservatives messing up my fluorescein patterns or my staining patterns on the cornea. And every time I put fluorescein on there, I get the exact same concentration, so that when it illuminates, the same amount of fluorescence means the same thing every time I do it. It's not variable. One of the things that makes reading fluorescein patterns so difficult is that it's never the same 2 times in a row. And a lot of that owes to the fact that we're getting different amounts of fluorescein concentration each time. So by doing this, one, it's quick. I keep one of these in my pocket, and I can pop it out and pop a drop on somebody's eye before you can tear open the strip. I'm done and on to the next thing. But you know, the number is I've had this photograph so long and the area code's not even on it. It's 214-349-8000, and that's Abrams Royal Pharmacy here in Dallas, and they've been making these in my lissamine deals for years. So we have lissamine and syringes in the exam room also. Okay, let's see. Patient follow-up. I see the patients fairly frequently to make sure that we're doing the right thing. And we also take post-keratometric readings to make sure I'm not warping patients' corneas. All these topographers will do difference imaging. And so you can take an image before you prescribe and then after you dispense and see if you're warping the corneal surface. I think those are important things that we often overlook. Troubleshooting. Almost always the problems that we get into with troubleshooting in contact lens, in my opinion, is that we don't have the back surface geometry correct. When we get our alignment done, then we can figure out our optics problems. I just don't even, I try to get the optics pretty close because the optics have to be fairly close to the lens dynamics to work right, but I'm never too worried about the optics of a lens until I'm certain I have the back of the lens correct. And then you really need to check and control for rotation. And part of doing that is make sure you order your lenses with markings on them so that you can see them. You know, in the old days when we used to dot the meridians, you could look at a patient and sometimes see multiple dots on. But now that we can laser etch a lens, you can put all kinds of things all over the surface of a contact lens, and nobody can see it but you when you look at them with a slit lamp. And always compensate for residual astigmatism. We do spherocylinder over refractions, and we add that in obliquely crossed fashions to the lenses, and you can do that easily. There are iPhone apps for that. You know, you don't have to think about it anymore. You can just sit there and do it, and there's no excuse for it because the calculations are now very simple, and the lathes can do exactly what you want them to do. So with that, I think we'll start concluding, then we'll take a couple of questions, and we'll be done. Be aggressive in aligning the back surface. Go to toric geometries early. The new fabrication allows you to do that. Be confident in correcting residual astigmatism. Use a spherical power effect whenever possible, and profit from your expertise. These are specialty lenses, and you should be charging accordingly. So with all that said, I will turn it back over to you guys for questions, and support the GPLI and patronize the CLMA member labs.
Thanks, Clark, and that reminded me to thank you for your column in the October issue of Spectrum on the GPLI. We really appreciated that. That's wonderful. We do have some questions. I was going to make a couple comments first. One is to remind people, and our project manager, Christy Deal, who administrates these webinars, reminded me to mention this to you all, that we do have a GPLI symposium on spherical and special design lenses, very clinical. That's in Oak Brook, Illinois, a suburb of Chicago, on Sunday, December 11th. And it really is kind of a how-to A to Z program. It's, I believe, 7 hours of CE, and anybody who'd like to can sign up easily on our website. Also, the comments that were made, I love the fluorescein delivery system. That's the first time I've seen Clark give that, and that's really cool. I couldn't imagine that, and yet that regulate fluorescein like that is that's really a blessing. The other comment I'll make is that to use a toric diagnostic set, and they, for example, on the SBE designs, you can get a variable amount of toricity on the back surface of the trial sets. That is a great way to fit. But knowing in the real life situation, you know, many people don't have trial sets and they'll go empirical. It's also important to mention not only is the manufacturing much better today and you can feel confident in the designs you get back, but there's several studies that have found empirical fitting of torics to be very successful. I know Langis Mashad published that article in Optometry 2 years ago, and also the Northeastern States University group several years ago on Mandel Moore, and found great success. So we're really seeing a lot of improvements there. I love the comments about using a low refractive index material. That makes perfect sense for many reasons. That brings me to the question I have, is that when we look at the fact that there can be a varied amount of residual astigmatism, and you have to think about there being maybe a third more refractive toricity than corneal, and then you have to factor in the refractive index of the material. Let me ask you this question, Mark. Are back torics really something we should use or use very often?
Probably not very often, but here's the neat thing about the guides, is that if you use either the Mandel-Moore guide or my modified guide, whether you end up with an SPE, a CPE, or a base toric lens, it doesn't matter because it comes out in the wash. It is whatever it ends up being. And so, you know, you might put together what you think is a bitoric lens by using the guide, when at the end of the day the lab guy looks at it and goes, oh, those two optical meridians are the same curve. So we'll put a spherical front on the lens, and you end up with a base toric even though you think you've got a bitoric. But you have to work through the math to get there. They do it easily because they have the CAD systems attached to the lathes. You know, they just put the numbers in and the CAD kicks the lens right out. But so I try to think conceptually about whether I think I'll end up with an SPE or not. But I can't remember the last time I actively said I'm going to use a base toric lens. Line up the geometry, put the powers in the calculator, and let the front surface come out in the wash. It'll either be toric or it'll be spherical.
Yeah, that's a great comment, Clark. I really hadn't thought about it that way, and I'm a little embarrassed that I haven't. But yeah, they can look at the powers, they can look at what's going to be there, and go, yeah, this is a case where we can use a back toric. And I think your worksheet and Tom Quinn's calculator that we have on our web, basically will come out with a design that can. I know Tom's will say use a back toric in this particular case, and when you factor in the material, that really helps as well. No, good comment. We had a couple questions. One was, and I know I really don't truncate anymore. I used to all the time, and used to do it in office, in fact, because Dr. Borish taught us how to do that. But do you, that was the question, is what do you truncate anymore? Do you truncate very often anymore?
I will truncate a lens when I can't control the rotation of a lens, either through ballasting or through toric curves. I made a scleral the other day. It wasn't truncated, but one of the things that people don't think about is you can put a periballast with a numeric control lathe. You can put a periballast on a lens that has toric surfaces. So to control rotation, you can have the toric alignment of the back as well as a periballast. So you can do multiple things. I had a rigid toric multifocal that we did on a patient a month or so ago that we ended up putting a truncation on. So I don't do it very often, but it's one of those tools, and I think what makes us experts is having multiple tools available and knowing when to use them. But just having that arrow in the quiver is helpful. And yeah, I used to do a lot of truncation myself. But when you truncate a lens, you're essentially abandoning lid attachment, because if the lens attaches to the upper lid, the truncation doesn't do anything except alter the prism.
Yeah, that's good. I think I'm unmuted, Mark. No, I think that's good. What's interesting about the truncation is when we learned it, and I won't bore everybody, but Dr. Borges' rule was always when if you had a high minus lens, you didn't need very much prism ballast, but then if you truncated it, it was almost, then you had as much as you would have on an untruncated plus lens or something. So you really had, it's interesting how you approach truncation. There's a question that is, how long after you dispense a lens do you prefer to check for corneal warpage?
Every visit. Once they're up to their wearing time. If they're adapted, if they're wearing a lens more than a couple hours a day, if you're not doing things right, you can warp a cornea very quickly. I mean, think about what we do with orthokeratology. Sometimes an hour of lens wear in the morning changes the shape of the cornea for the whole day. You do that for 4 or 5 hours a day, and you're going to warp a cornea permanently. So we're checking every time, and we're also correlating it with their spectacle prescription. I mean, if I design a lens for a patient and I don't change their glasses prescription one lick, I think I'm doing a pretty good job of aligning the back of that lens up. Because remember, it's a geometry problem. And if you get the geometry right, you won't change the geometry of the cornea.
All right, very good, Mark. To answer Kenneth's question, we should have this webinar recorded, so we'll get back to you in terms of your question. Thank you. In fact, thanks everybody for some very good questions. I think at this point we can probably bring the webinar to a close. I really want to thank Dr. Clark Newman, who is just an outstanding clinician. He's one of the best clinicians I think we have in the country, and he really gave a well thought out modern contemporary lecture on a very important topic, and one that, just based on the questions, people have quite an interest in. And we can never abandon the bitorics. And if you really look at the Coke Pepsi test versus soft toric patients who are having difficulty, always remember that's a viable option and actually becoming an easier and easier option to use based on some of the nice calculators that we have today. So with that, again, I want to thank Dr. Newman for an outstanding presentation. I want to thank you all for attending tonight, and have a good night, and we'll look forward to seeing you again in a month when we have GP Lynn's Case Grand Rounds with Dr. Barry Iden. So thank you again, everybody, and have a good night.